Hello everyone, welcome to the lecture 4 in the course Diffusion in Solids. Today, what we are going to do, so in the last class, what we discussed was the Fick's laws of diffusion. We saw the Fick's first law, we saw the Fick's second law, equation of continuity, and I told you that these laws are very important when we want to solve any diffusion related equations. Now, typically, when you are trying to solve or arrive at a mathematical solution for a diffusion-related phenomena or a diffusion-related problem, the mathematical form is in the form of differential equations. So that means that for any problem, the mathematically, when you formulate the problem, you will see that you arrive at a differential equation, which needs to be solved. Now, we also saw in the relevant mathematical concepts lecture some ways to solve the differential equation. However, there is another important method which I wanted to dedicate a separate lecture today and a little bit more applied to the Fick's laws in the next one, which is very relevant for solving the diffusion related equations. So that method is known as the Laplace transform. So today we will be seeing how do we define the Laplace transform, some of the properties of Laplace transform, and I will also give you some example of how to solve the initial value problem. Now, actual application of Laplace transform to the diffusion related equations we will see in the next lecture, but today's lecture is very important in a sense that you will get a feel of what is Laplace transform, how to evaluate the Laplace transform of various functions. So basically, any transform, an integral transforms as we call it, they are an important tool for solving differential equations. So any integral transform in general can be written as f of s equals to integral alpha to beta k of s comma t ft dt, where this k of s comma t is the kernel of the transformation. It is known as kernel of the transformation. So this k, alpha and beta, they will vary depending upon what transform we are looking at. So if you are looking at Fourier transform, these values may be different. Now we will see about the Laplace transform, what these values are. So as I said, alpha and beta, they can take the values like minus infinity, infinity, both of them, and so on. And the capital F is called the transform of small f. So in this lecture, or in this course rather, we will be only talking about the Laplace transform. So in general, any solving of a differential equation, depending upon the nature of the differential equation, you take this small function f, you transform it to a function capital F, which is the transform of small f, and this capital F function is usually easier to solve. And once you solve using the techniques, some of the techniques we will talk about, you find what is this capital F, and then you do an inverse transform to find your original function, that is small f. So this is in general the strategy for any integral transforms. So basically you are taking a function, you are transforming it to a function which can be a little easily solved, and then you find the function. Once the solution of this transformed function is found, then you do a inverse transformation to find your original function. So now coming to Laplace transform, how do we define it? So we define it, we can define it L of f of t is equal to capital F of s. So s is a variable here, is equal to 0 to infinity e power minus st into ft dt. So you see here, if you compare this equation here, let me use the laser pointer. So if you compare this equation, this integral here with this, you will understand that e power minus st is the kernel of the Laplace transform. and in this case alpha and beta are 0 and infinity respectively. And this type of Laplace transform, this Laplace transform is very useful for solving differential equations with constant coefficients. So then let me show you some examples on how to evaluate the Laplace transform. Basically, it involves solving the integrals. Some of the concept of solving integrals we have already covered in the lecture 2. So let us say one example where f of t is the simplest function you can imagine, which is a constant function, and this constant is equal to 1. So f of t is 1 where t is greater than or equal to 0. Then the Laplace transform of f of t can be written as 0 to infinity e power minus st. Ft is 1, so it will be simply e power minus st dt. Now, if you recollect what is the integral of this exponential function, so e power minus st is e power minus st, and because there is a minus s here, and which is not the integration variable, so it will be just treated as a constant here, and you have to divide it by minus s. So the integral is e power minus st by minus s, and you put the limits as 0 to infinity. So if you put infinity here, e power minus infinity is 0, and minus, when you put 0, then e power 0 is 1. So overall the answer you get is 1 by s. That means the Laplace transform of the function f of t, or Laplace transform of 1, is 1 by s. Let us look at another example, which is where the f of t is e power at, again t is greater than or equal to 0. Now Laplace transform of f of t would be 0 to infinity e power minus st into e power at dt, which is equal to 0 to infinity e power minus s minus at dt. Remember again here the integration variable is t, so s minus a is like a constant here when you are evaluating this integral. So if you follow this particular example, then again the integration will be e power minus s minus a by minus s minus a from 0 to infinity, and if you put the limits, what the answer you will get is 1 by s minus a. So hope this is clear. Let us take the third example, which is slightly more longer process of evaluation. So let's say your function is equal to sine of at, where t is greater than or equal to 0. Now L of f of t, which we can call it as the capital F of s, is equal to 0 to infinity e power minus sine e power minus st into sine at dt. Now how do we solve this integral? So if you recollect the lecture on the mathematical concepts, then we understand that here this can be solved by using the integration by parts. Now when you are using the integration by parts, this we take as the function here as the first function. So basically here you have e power minus st. Integration of sine at is cos at by a with a minus, because integral of sine is minus cos. So you have minus cos at by a, and 0 to infinity is the limits for this integral, minus the integration of 0 to infinity of this quantity multiplied by the differential of e power minus st. So I suggest you can once again look at the formula for the integration by parts, and therefore now you have 0 to infinity. So the differential of e power minus st is nothing but s into, or rather minus s into e power minus st, and the integration of sine at, as I told before, is minus cos at by a. That's why you don't see minus here, because there is one minus coming from the differential of e power minus st, another minus coming from the integration of sine at. So therefore the minus minus cancels out, So what you have inside the integral is s into e power minus st cos at by a. Now again here in the first term, if you put infinity here, then e power minus infinity becomes 0, minus here if I put 0, this terms become 1, and cos 0 is also 1, so you have minus 1 by a. Minus s by a can come out of the integral because the integration variable is t. 0 to infinity e power minus st into cos at dt. Now this again cannot be solved directly, so we have to again apply the integration by parts. So now the f of s becomes 1 by a minus s by a 0 to infinity e power minus st cos at dt. So what it means is that we have to apply one more time the integration by parts. So if you apply this integration by parts again, what you get is f of s is equal to 1 by a minus s by a. Again, e power minus st is the first function. Integral of cos at is sin at by a. Remember, integral of cos is a plus sign, so there is no negative here. From 0 to infinity minus integral of 0 to infinity. Integral from 0 to infinity, inside the integral you have the differential of this e power minus st, which is minus s into e power minus st, and the integration of the cos, which is sin at by a. Cos at is sin at by a, and dt is there. So this minus, when it goes out, it becomes plus. So you have f of s is equal to 1 by a minus s by a. So if you put infinity here, then e power minus infinity is 0. When you put 0 here, the sign of 0 is 0. So this whole term goes to 0, plus s by a 0 to infinity e power minus st into sin at dt. And now what is this? If you see, this is our original integral, which is f of s. So f of s now can be written as 1 minus a. This s by a comes here, so s square by a square into f of s. This was the original f of s. So if you take it this side and bring the denominator here, then you will get f of s is equal to a by s square plus a square. So basically the integral or the Laplace transform of sin at is nothing but a by s square by plus a square. Actually, strictly speaking, we should write whenever we are writing an integral of the form a to infinity f of t dt, we should write it as limit of a to infinity, capital A to infinity, small a to capital A f of t dt. However, in the examples that we are going to deal with, and later when we solve the diffusion related problems, this will not matter so much, but please keep in back of your mind that the very strictly the way of writing is this way. Now, let me tell you one important property of Laplace transform, which may seem at first a little trivial to you, but we seamlessly use it without even realizing that we are using this powerful property, which is that Laplace transform is a linear operator. What it means is that if I have two functions, let's say f1 and f2, where the Laplace transform exists for s greater than a1 and s greater than a2, then any linear combination of f1 and f2, suppose there is c1 f1 t plus c2 f2 of t, their Laplace transform can be simply written as c1 Laplace transform of f1 t plus c2 Laplace transform of f2 t. So this means that Laplace transform is a linear operator. So essentially what it means is that if I want to, let's say we evaluated the Laplace transform of sin at, it comes out as a by s square plus a square. Now if I have to evaluate the Laplace transform of, let's say, 2 sin at, that means it becomes 2a by s square plus a square. So the constants can simply come out. Now let me tell you another important theorem which is useful when we talk about the Laplace transform. Of course, there is much more depth in which people go and use the Laplace transform. We are going to restrict ourselves to what is more relevant for the diffusion related problems. So this theorem states that if f is continuous, if f is a continuous function and f dash is at least piecewise continuous on any interval 0 and a, so that means where t lies between 0 to a, and suppose there exist constants such as k, a and m, and satisfy mod of f of t is less than k dot e power a t for any t greater than or equal to m, then the Laplace transform of f dash of t exists for any s greater than a. You don't need to worry about just for this particular lecture. So this particular condition are more strict mathematics, but as far as the examples that we will be taking in this course, most of the time you will find that these conditions are satisfied, but it is still a good idea to at least check whether f is continuous and f dash is at least piecewise continuous. We defined these terms in the lecture 2 already. So then the important relation for us actually is that if you want to find the Laplace transform of f dash of t, you can find it in terms of the Laplace transform of f of t, and you can use this relation. So the Laplace transform of f dash of t is equal to s into Laplace transform of f of t minus f of 0. So once again I will repeat, Laplace transform of differential of f of t, that is f dash of t, is equal to s dot or s into L of f of t minus f of 0. It also can be extended to the second derivative. That means if f dash and f double dash satisfy the above conditions, then we can also write L of f double dash t is equal to s square into L of f of t minus s of f of 0 minus f dash of 0. So these two relations we will be making use when we solve the initial value problems. Now these are some Laplace transforms of the sum of the key functions that I have given here. It will be useful for you when you solve the more problems on them. Now let us take a couple of examples of solving the initial value problem using the Laplace transform. So the first problem is y double dash minus y dash minus 2y is equal to 0, and given the initial conditions are y of 0 equal to 1 and y dash of 0 equal to 0. Now assume that this problem has a solution represented by y is equal to phi of t. Now what I can do is I can take Laplace transform on both the sides. Again, so the Laplace transform of y dash y double dash minus y dash minus 2y is equal to Laplace transform of 0, which is 0. And again, using the property of the linear operation, we can write this as simply L of y double prime minus L of y prime minus 2 L of y is equal to 0. Now, just in the previous slide, the theorem that we used, it allows us to split these two like this. So the L of y double prime can be written as s square L of y minus s dot y of 0 minus y dash of 0. Similarly, L of y prime can be written as s times L of y minus y of 0 minus 2 Ly equal to 0. And just for the convenience, I write f of s, L of y, I write as f of s. So if I collect the term which has f of s, which is here, and here, then it becomes s square minus s minus 2 into f of s. plus this, if I collect the term containing y of 0, then 1 minus s into y of 0 minus y dash of 0 equal to 0. Now, we already are given that y0 is equal to 1 and y dash is 0 is equal to 0. So, s square minus s minus 2 into f of s plus 1 minus s is equal to 0. So, which tells us that f of s is equal to s minus 1 s square minus s minus 2, and this can be splitted into fractions as s minus 1 by s minus 2 into s plus 1. Now, you can use the method of partial fractions to split it as following, that f of s can be written as 1 by 3 s minus 2 plus 2 by 3 s plus 1. Now, we know that we have seen in the first example that the Laplace transform of e power at is 1 by s minus a, or in other words, if I want to find the inverse of the 1 by s minus a, the Laplace inverse of 1 by s minus a, it will be e power at. So now, if I take the inverse of this f of s, which is nothing but phi of t, this is equal to inverse of this. So, inverse of 1 by 3 s minus 2 is nothing but 1 by 3 e power 2t plus 2 by 3 e power minus t. Why minus is coming? Because this is s plus 1. So, this is saying like s minus minus 1. So, a is minus 1 here. So, this becomes 2 by 3 e power minus t. So, this is the solution of the differential equation. You can very well check whether it satisfies the initial conditions. You put 0, so you will get this term as 0, 1, this term as 1, you will get 1 by 3 plus 2 by 3, which is equal to 1. Then one more example I can show you, which is basically here. So, if you solve y double dash plus y is equal to sine 2t, given that y0 is equal to 2 and y dash 0 is equal to 1. Again, let us assume that y is equal to phi of t. Take the Laplace transform both the sides. So, using the linear operation property, we can write L of y double prime plus L of y is equal to L of sine 2t. So, L of sine 2t, as we saw, this L of sine at is a by s square plus a square. So, which is 2 by s square plus 4. Now, using the theorem that we have seen a couple of slides back, you can write L of y double prime is equal to s square into L of y minus s times y of 0 minus y double dash 0 plus L of y is equal to 2 by s square plus 4. Let us call L of y as f of s. So, this becomes f of s into s square plus 1. So, here you can see s square plus 1 minus s times y of 0 minus y dash of 0 is equal to 2 by s square plus 4. Now, if you put the initial values of y 0 and y dash 0, what you get is f of s into s square plus 1 minus 2s minus 1 is equal to 2 by s square plus 4. So, f of s, you can, if you do some algebraic basically rearrangements, you get 2s cube plus 8s plus s square plus 4 plus 2 by s square plus 1, s square plus 4, and you have s square plus 1 here. So, finally, your f of s is equal to 2s cube plus s square plus 8s plus 6 divided by s square plus 4 and s square plus 1. Now, when you want to basically separate this using partial fractions, you perhaps know already that such a function can be splitted as f of s can be written as as plus b divided by s square plus 1 plus cs plus d divided by s square plus 4, which is equal to 2s cube plus s square plus 8s plus 6. And now you again do algebraic rearrangement, and then this two terms will cancel out from the denominator. What you have is as plus b into s square plus 4 plus cs plus d into s square plus 1, which is equal to 2s cube plus s square plus 8s plus 6. And if you take the terms which have s cube, for example, here this a and here is c, so a plus c into s cube. Similarly, b plus d into s square, 4a plus c into s, and 4b plus d is a constant term and equated to the RHS. Now compare the coefficients of the like powers of s. That means s cube here, for example, will tell you that a plus c should be equal to 2. Similarly, here if you compare b plus d should be equal to 1, 4a plus c is equal to 8, and 4b plus d is equal to 6. These are very simple equations, and if you solve, you get a is equal to 2, c equal to 0, b 5 by 3, and d is equal to minus 2 by 3. So now if you put these values, which means that f of s is equal to 2s by s square plus 1 plus 5 by 3 by s square plus 1 and minus minus 2 by 3 by s square plus 4. Remember that c is equal to 0. Now again you take the inverse of this. So taking inverse, we know about this quantity. When it is a by s square plus a square, it is the Laplace of sine at. When it is s by s square plus a square, it is actually the Laplace of cos at. It is given in the table also. So this tells us that the solution, that is f of s, the inverse of f of s is equal to phi of t, which is our original function, should be equal to here 2 times s by s square plus 1 Laplace inverse would be cos t, plus, see, remember that this is s square plus 1, which is, that means that a is 1. So that's why 2 cos t, plus again here also a is 1. So you have 5 by 3 sine t, and here a is 2. So you get minus 2 by 3 into sine 2t. So there is a small mistake here. It should be written as 2 by 3. Let me just. So this should be minus 2 by 3 sine 2t, because here the value of d is minus 2 by 3. So this is basically the solution to the differential equation that we started earlier with. So this is what we wanted to cover today. So in the next class, we will see how do we apply this Laplace transform to fixed law, and then later on to solve the diffusion related equations. Thank you.